If you've ever taken an EV on a road trip, you've probably experienced terrible, well below advertised range, and you might be surprised to hear that wind has one of the biggest impacts on range, and in this video, we're going to explore exactly why. So before we quantify exactly how much wind impacts range in any car, first let's define what wind is. Obviously, if you've ever been outside, you know what wind is, you've felt it before, or if you're driving on a high-speed highway, sometimes you can feel when the wind really picks up, the car is a little bit unstable. But we're going to simply define wind as a vector, which basically means it has a direction and a magnitude. And we also know that wind gusts, so it's not necessarily constant. It can come from one direction, and then 5 minutes later, it can switch directions and come from the exact opposite direction. Let's talk about air resistance. Air resistance is the force acting opposite to the relative motion of any object moving with respect to a surrounding fluid, aka air. This might be a mouthful and sound complicated, but all this is saying is as a body goes through a fluid, there's forces that act on the body. And the fluid in this case is just air. It follows a pretty simple formula. Force of air resistance is equal to 1/2 rho, which is air density, multiplied by the coefficient of drag, multiplied by the frontal area of the body. In this case, it's just the frontal area of the car, multiplied by v squared, which is just the velocity in meters per second. Let's calculate a really quick example just to give you an idea of the numbers involved here. So we're going to use a Model 3 long range, which has a coefficient of drag of 0.23 and a frontal area of 2.21 square meters. At 60 miles an hour, which is 26.8 meters per second, the force of drag is 1/2 multiplied by rho, multiplied by the coefficient of drag, multiplied by frontal area, multiplied by v squared. If you plug in all the numbers, you see that the force of drag is about 220 newtons, or about 49.3 pounds of force. Cool, so you now know the basic definition for wind and air resistance, and you know how to calculate air resistance for any given vehicle. Let's now see exactly how wind is going to affect the vehicle. So first, we're going to assume that we have a car driving at 70 miles an hour on the highway. It's going to be driving due east, and we're going to hit it with a headwind. So at the top of the screen, you can see a compass, and we're going to say that this wind is 10 miles an hour coming in the direction of west-southwest. I've gone ahead and circled it on the compass so you can see what that direction is. So we have our wind speed, it's 10 miles an hour west-southwest, and we have our car speed, it's 70 miles an hour due east. And so we know that the angle of wind is actually 22.5 degrees relative to the front of the car. I've drawn the triangle in the bottom right there. And with that triangle, we can actually find the x component and the y component of this wind vector. And it's really simple geometry. You basically take the cosine of the angle and multiply by the magnitude to find the x component, and then you just take the sine of the angle and multiply by the magnitude to find the y component. And another way to think about that x component is the amount of wind that's hitting exactly opposite to the motion of the car. Cool, so we know that about 9 miles an hour of wind is hitting the car head on, and we know the car is traveling at 70 miles an hour. But what does this mean for the overall air resistance equation? Since air resistance is a relative calculation, you have to actually add wind speed onto the velocity of the car. So we're going to use the exact same equation as before, except we're going to swap out all the variables except velocity with a constant k. So you can see force of drag is equal to k multiplied by velocity squared. So with no wind traveling at 70 miles an hour, the force of drag is equal to 31.29 meters per second squared multiplied by k, which comes out to 979 k. Then we're going to add wind, so we'll use our 10 mile an hour wind example, and that comes out to 1254 k. So traveling at 70 miles an hour with our 10 mile an hour headwind from the example multiplies the aerodynamic forces by 1.28 times. So the huge takeaway from walking through that example is that wind actually increases the force of air resistance that's acting on the car. And that's because wind changes the relative airspeed, which is the huge component of that air resistance equation. It's that v squared component. So that's cool. We're talking about forces and we're talking about wind. But what does that mean for the actual efficiency of the vehicle and how much power it's consuming? So what we can do is actually convert the forces that act on the car into power needed to overcome those forces. So in order to calculate power, we need to know all of the forces acting on the car. We already walked through air resistance, you know exactly how that's calculated, but the second force that acts on a car as it drives down the road is rolling resistance. This is a friction force between the tires and the road, and it takes the formula force of rolling resistance is equal to the coefficient of rolling resistance multiplied by the normal force. And the normal force is just the weight of the car. So if we use the really simple power equation, power is equal to force times velocity, we can actually multiply our velocity by the sum of those two forces. So we see our final formula below. We see that power is equal to the force of air resistance plus the force of rolling resistance, all multiplied by how fast the car is going, the velocity. So we're going to walk through another example with our same Tesla Model 3. You know how much I like examples. So our power equation is 1/2 rho multiplied by velocity squared multiplied by CDA multiplied by velocity plus coefficient of rolling resistance times normal force times velocity. So all of that is going to give us how much power we need to overcome forces at any speed with wind included. So in this example, we're going to be driving at 60 miles an hour, and we're going to say there's wind speed of 10 miles an hour that's acting directly on the front of the car. So we plug in all the numbers, and we see that power needed to overcome those forces is about 14.5 kilowatts. And if we take into account how EVs are not perfectly efficient, generally there's about an 80% battery to wheel efficiency due to various losses. We see that the actual power output from the car is closer to 18 kilowatts under these conditions. Instead of walking through a ton of examples, I did all the math for you. So you can see this nice clean chart here. We have the speeds 60 miles an hour, 70 miles an hour, and 80 miles an hour. And from left to right, we have no wind, 10 mile an hour tailwind, and a 10 mile an hour headwind. It's pretty amazing how just a 10 mile an hour wind can shift power required by literally 20 to 30%. And this factor is actually squared. So if you add 20 miles an hour of wind or you remove 20 miles an hour of wind, the power required is going to change even more. So what does this mean for overall range of the vehicle? Well, I'm going to stick to our Model 3 long range example. It has about a 75 kilowatt hour battery pack, and we can take all of our power conversions from earlier and convert them into range. So we have the exact same table setup, and you can see the figures there. If you compare a 10 mile an hour tailwind versus a 10 mile an hour headwind, that can impact your range by almost 50%, which is just crazy. So imagine driving at 80 miles an hour and you get hit with a 10 mile an hour headwind. The calculation from air resistance is going to be like you're driving 90 miles an hour. And so your range could drop from somewhere in the mid 200s to well below 200, something like a 20 to 30% drop. And that's only a 10 mile an hour headwind. Imagine if that wind increases, your range is going to go down very quickly. So what did we learn from going through all those tables? Air resistance is equivalent to velocity squared. So multiply your velocity by 2 and you multiply your force of air resistance by 4. So the faster you go, the more and more power you need to overcome those forces. And there's one more thing, which is you cannot average wind speed when taking it into account. So I'll lay out a really simple example. Let's say you're driving an hour at 60 miles an hour with a 10 mile an hour tailwind. So the wind is actually going to be helping you in this case. You use 10.65 kilowatt hours of energy, and then you're going to turn the car around and go the exact opposite direction. So now you have a 10 mile an hour headwind. And that takes 18.07 kilowatt hours of energy to drive for that distance. And if you sum up the energy used to go there and back, it's 28.72 kilowatt hours. If you compare that to just driving for 2 hours at 60 miles an hour with zero wind, that's only 27.5 kilowatt hours of energy. So the average wind speed on your windy trip is 0. And your average wind speed on the trip with no wind at all is 0, but you use more energy on the first trip because when you're going there, that headwind is actually going to be a factor squared, and that's going to use way more power than the reverse. And so my whole point here is because the aero force that acts on the car is correlated to the velocity squared, you can never average wind speed. So if you're going to do some sort of round trip in a car and it's really windy, you can assume that you're going to get far worse range in general, even if you're doing a perfect round trip and the wind doesn't shift, than if there was no wind at all. So the whole conclusion I'm trying to get across is wind almost always makes consumption worse unless you're driving with a really consistent tailwind. And if you want to see this for yourself, I created a little efficiency simulator. I'll put a link in a pinned comment below, but you can select from a few cars, play around with the headwind and different parameters and see how that affects power and range. So check it out for yourself. If you like the video, make sure you hit that like button and subscribe. I'll see you guys next time.